Okay, we're gonna go ahead and start off this hours a little bit early today since you're all here already. What questions do we have?
13.
Number 13.
I have 15J.
Number 15, part J.
14.
Put 14 in there. 13, 14, 15 are definitely the hard ones of this homework. And I think, I can't remember if it's 13 or 14, but one of them's not quite fair for this midterm.
14.
Or sorry, for this quiz.
Wait, you said 13. You said 14 in the video.
In the video, I think it's 14. 14 is essentially a repeat of the lab you did this week. Or that you're going to do this week. Or you just did, depending on where you are. 13, 14, 15, last part. Any others?
Number 6.
Number 6.
4.
Any others? What just happened to my video? It went blurry. Oh boy, I was worried that was going to happen. Hang on. Number 6. Any others we should think about?
4.
How did autofocus get turned on?
19. Yeah.
There we go. Okay. What was that last one?
4 and 19.
4, 19. That should be a good start. Let's go ahead and get started. What is problem number 4?
Wait, let me look at that.
Everyone go ahead and pull your homeworks out.
It says a beaker with 250 milliliters of an acid solution with a pKa of 5.45 has a pH of 3.
pH equals
pH of
3.
3.
And 250 milliliters. Oh, I'm not gonna write that. And then part A says what is the concentration of the acid?
So in most of these problems, so whenever we're dealing with an acid in a beaker where it's just an initial acid problem, we almost always end up getting the same equation. We could set up the ice table for our generic acid, do products minus reactants, get our equilibrium, all of that. But we almost always get Ka equals x squared over the initial concentration of the acid, where x is going to be equal to the concentration of A minus, and it's also going to be equal to the concentration of H3O plus because of the 1-to-1 ratio. So almost always what happens in these problems is we are given one of the 3 variables. We're either given the percent dissociation, which tells us the A minus. We're given the pH, which tells us the H3O plus. That gives us our X. We're given the Ka, or we're given the concentration. The ones that we've been doing in class have mostly been, I give you Ka, I give you the initial concentration, I ask you to find the H3O plus. Right? That's the forward way to do it. But any problem we can do, we should also be able to do backwards. So, in this problem, we just have to identify, it's an initial pH problem, it's just an acid and water, so an equilibrium problem, and then we have to identify which variables we're given and which variables we're trying to solve for. In this case, we're given the Ka in the form of pKa, we're given X in the form of pH, and we're asked to find HA. So we plug these in. I'm trying to think of a way where I don't have to do like the negative logs things. So if I take, I want to do some algebra. Should I do algebra or should we just use our calculators? Let's just use our calculators. Get your calculators out and go ahead and calculate this. Let's get what our HA initial concentration. And notice the problem should have said what is the initial concentration, not just what is the concentration. Kind of implied. While you all do that, I'm going to do something weird. Don't worry about it.
Go over how you're using those to find like the X.
So if we take 10 to the power of negative 3, it'll give us our H plus concentration. If I do 10 to the power of negative 5.45, it'll give me my Ka. Don't worry about what I'm doing on the board. I just want to see if I can do this. Oops. Or you can use this equation via algebra. Right, I just took the negative log of both sides, and I can say pKa equals 2pH plus log of HA initial. Then I don't have to do 10 to the power stuff, right? I can do 5.45 minus 6 is equal to log. I don't know if this is going to work. It's just algebra, so it should work. I'm doing it in yellow to kind of say, look, this is weird. 5.45 minus 6 is 10 to the negative 0.55. So you all do it your way. I'm going to do it my way. We're going to see which. We should get the same answer. These should be mathematically equivalent to each other. Of course, I picked a calculator that doesn't work. 0.281?
For what?
The concentration of HA. Final answer. Ta-da! So, forgetting all the stuff we did in yellow, you can just do your regular mathematics, and you get 0.281 molarity. That's your initial concentration. Yeah?
Do we need to divide by the 250 milligrams?
No, because it's just asking for concentration. It turns out in this problem, the 250 mils is completely extra information. If at some point it asked how many moles, or it asked what kind of reaction, if it was doing something where we needed moles, then we'd need that 250. But in this case, it's excess information. I do want to point out that we can essentially make something that's Henderson-Hasselbalch-like. pH equals pKa minus log of HA divided by 2. Right? This would be an equation that's like the Henderson-Hasselbalch equation for the initial pH, right? The Henderson-Hasselbalch equation is essentially derived the same way, where we've got the ratio of conjugate base, weak acid, H3O+, you take the negative log of both sides, and you get something that makes a kind of simpler equation, right? We can also just do the ice table and do the equilibrium and plug everything in, but just by taking the negative log of both sides, I can get this equation. And notice it still has my same features. I have my H3O+ concentration, my Ka, and my initial concentration. I'm going to put an I on there to specify that it's initial. So I still have my 3 unknown variables. It just takes on this weird looking form because of going to the log scale. And that's just for part A. What happens for part B?
Should I read part B?
Yeah.
It says, if you were going to make a solution with the same concentration that has a pH of 2, what should the pKa of the acid be? And what are some acids with possible pKa values necessary to make this solution?
Notice, we've got the exact same situation, except for now we've changed which information you have. Right, we still have the pH, which is going to give us our X value. We still have the HA initial. And now we're being asked to solve for the Ka. After we have that Ka, we're supposed to look at a table, like in the back of the textbook, and figure out what acids are close to that Ka. But it's the same thing, so I'm gonna let you do that on your own, and we're gonna move on to the next problem, if that's okay. And if everyone can scoot in just a little bit more, there's a couple people stuck in the hallway, and I want to make sure they're seeing this if they want to. Ready to move on from problem 4? There's space here, there's space here. I'll at least make them. Okay, so that was
Wait,
number.
I have a question.
Yeah.
So you just use the same Ka from the part A?
No, we're solving for the Ka in this case, right? In part B, we're trying to figure out what acid would give us 0.01 squared divided by 0.281. Right, and we're solving for the Ka, right? We're flipping the problem. Out of our three variables, we're switching which is the unknown variable. But it's almost always that same type of idea of we have to identify what equation we're using, which parts we know, and which parts we're trying to solve for, right? Problem-solving skills. It's always going to be approximately the same. Ready for number 6? Somebody else do me a favor and read number 6.
Write the reactions for the following bases and write the expression for the Kb equilibrium constant.
How many parts are there?
It's 4.
But
Let's-
they're all the same.
Let's pick 2. Let's do the last one. No one does the last one, right?
Hydrogen phosphate and
Is it
H2PO4.
dihydrogen phosphate? So we're going to look at this acting like a base. Now notice we've got a compound that can behave like an acid or a base. However, this problem is specifically asking for us to see how it behaves like a base. So if I'm going to have this behave like a base, it is going to be a proton acceptor. I'm going to get H3PO4, taking that proton from water. This is aqueous. Always remember your states of matter. Aqueous. And I'm also going to get some OH minus, because out of that water, which is liquid, I've got that. That is the equilibrium reaction for H2PO4 minus acting like a base. And then I can say the Kb for this is just going to be H3PO4, my conjugate acid, my hydroxide, and my weak base. I think if you look at number 5, it does the exact same thing, except for it has this behaving like an acid. Remember, in this idea of this thing can be an acid or a base, and we can call it a conjugate acid or a conjugate base, gets into the kind of interesting definitional ideas we get to with the Bronsted-Lowry definition. Is compounds can be proton donors and proton acceptors at the same time. And then it's just a matter of how well does it do those two things in the conjugate pair. How well does it donate protons? How well does it accept protons? And what we'll find as we start to talk more about buffers is that's what gives you can kind of control whether it's donating protons or accepting protons by going to the correct pH and controlling the pH with a buffer. So we can force this thing to be H3PO4 by making a correct buffer. Or we can force it to be HPO4 minus by creating the correct buffer. Is that good for number 6? Number 13. If I remember correctly, that's a big one. If someone has the printout, I'll just take a look at number 13, because that's a lot to read. So, number 13, we've got 3 buffers. Buffer A, buffer B, and buffer C. They're all ammonium buffers. So this is number 13. They are all some ammonium buffers. And the first thing, part A, is calculate the pH. So we're going to go with Henderson-Hasselbalch. pH equals pKa plus log conjugate base NH3 over weak acid NH4 plus. Now, if this is my weak acid, what's my Ka, or more importantly, what's my pKa? I'm going to need the Ka for NH4 plus. Did anyone look that up? I don't have it in my head. You're going to have to look at the Kb and convert it. It's going to be something like 5 times 10 to the minus 10.
KB for NH4 plus.
Oh, Ka. What's the Kb for NH3? So in order to get this, we're going to notice, because we're dealing with something that's really a weak base and it's conjugate acid, if we want to use the Henderson-Hasselbalch in the way that we derived it, we have to look at it in terms of NH4 plus as an acid, which means we need the Ka for this, which is going to be the Kw divided by the Kb for NH3.
The
Yeah.
Kb for NH3 I found is 1.8 times 10 to the negative 5.
Right? We know that the Kw is 1 times 10 to the minus 14. That's about 2. You're going to get like 5.5 times 10 to the minus 10. Someone help me out.
5.5.
So I'm going to go ahead and put that here, 5.5 times 10 to the minus 10. That's going to give us a pKa of
9.3.
9.3. Quick memory thing for all of you. I know I don't like to talk about memorizing things, but there's 2 things that I remember. The Ka for acetic acid is 1.8 times 10 to the minus 5. The Kb for ammonia is 1.8 times 10 to the minus 5. These are not the same things because one's a Kb, one's a Ka. I have accidentally memorized the Ka for acetic acid because it is the most common example of a well-behaved weak acid system. 1.8 times 10 to the minus 5. And then at some point, probably like 2 years after doing this dozens of times, I realized that the Kb for ammonia and the Ka for acetic acid are the same value numerically. That's how I can always figure that out. Like, I knew it was going to be something like 5 times 10 to the minus 10 because I've done this calculation so many times. Just a little aside. Now let's get back to doing this problem. So we want to solve for the pH. We've got buffer A. And I'm just going to write this down in terms of the ratios. We've got so all of these are going to be in terms of their NH3, NH4 ratios. Buffer A is a 1-to-1 ratio. It is 1 molar NH3, 1 molar NH4. Buffer B is 2 molar NH3 and 2 molar NH4. And buffer C is 3 molar NH3, 1 molar NH4. For each of these, I can calculate pH. This one I can pretty much do in my head, right? This is a 1-to-1 ratio. Log of 1 is 0. This is the midpoint. pH is equal to pKa 9.3. Guess what happens for B? Same thing, 9.3. Problem C? Not the same thing, right? Problem C, we've actually got a little bit of a difference. Notice I've got more base than acid. So I expect my pH to be higher. Yeah, I expect my pH to be higher than 9.3. How much higher? I'm going to do the log of 3. I don't know what that is in my head. And I'm going to add that to 9.3. I know it's going to be a number greater than 1 because the log of a number greater than 1 is, or it's going to be positive because the log of a number greater than 1 is positive. Yeah.
So how did we determine that we were going to use the pKa value of NH4?
So because I didn't want to try to come up with some like base version of the Henderson-Hasselbalch equation, which we could do the same thing we did in class between Wednesday and Monday. Write out the reaction, write out the equilibrium for a weak base conjugate acid system. But ultimately, anytime we're in a buffer, we get to pick whether we're looking at the acidic behavior of the conjugate acid or the basic behavior of the conjugate base in that conjugate pair.
Okay.
And we said, you know, it's going to be easier if we stick to the acid behavior because then it's all in pH and we're using the same Henderson-Hasselbalch.
Okay.
But if we're going to be looking at that acid behavior, I need the Ka for my ammonium.
Okay.
Did anyone calculate this?
9.8.
Great. That is what we expected, an increase in pH that is less than an increase of 1, right? Because if we went all the way up to 10.3, we'd be pushing out of our buffer region. That's part A. Part B. Ooh. Find the pH of each buffer. This is a. What's that?
Is that not going to be unfair?
I'm not going to say that. This is what I was going to say. This is. It's so easy once you know what to do, but it's hard until you figure that out. So, but the thing I was going to say is this is a great question to understand because it's also on your buffers lab post-lab activity. So this is something that you should understand, and it's really connected to that equation we looked at the end of class on Monday. Find the pH of each buffer after 0.1 moles of HCl is added. Which buffer has the smallest percent change? See the section in your text on buffer capacity and buffer range if you're not sure how to calculate the percent change. Find the pH of each buffer after 0.9 moles of HCl is added to the original buffer. How well did each solution buffer the pH compared to the others? For the original buffer solution, calculate the pH after 0.1 moles of NaOH is added. So it's asking us to add acid, add more acid, and then add base and see how it compares. So we're going to look at this, and if we are adding acid, what's happening? pH is going to go down because I'm looking for the R word. Starts with an R, ends with the action.
Reaction.
Yeah, reaction happens. So what's going to happen in this case is essentially I'm adding H+. I look at this and say, is H+ going to react with NH4+? No, it's going to react with my NH3. So I'm going to write this down as H3O+ plus NH3 goes to NH4+ plus H2O. This is a reaction, right? So I'm going to do my stoichiometry. I'm going to do my blah, blah, blah. We can then go ahead and after we do this reaction, start reaction access, I can recognize the fact that I have 1 liter of each, so my molarities are my moles. I'm then going to set up my equilibrium table. And I'm going to set up my equilibrium such that I want it to be in the Henderson-Hasselbalch. As long as I don't run out of one of my reactants, I should be able to set it up in terms of NH4+ plus H2O goes to NH3 plus H3O plus, and then I can set up my ice table, and we can do all of that. When we do all of this, we get that great equation I showed you in green last time. I'm going to write it a little bit differently, and I think it might work better for what we're looking at. I'm going to break it down in terms of a few more steps. pKa plus log. Let's see, this would be moles conjugate base divided by, I'm going to call it moles of conjugate base at the start, moles of weak acid at the start. Now, if I'm adding acid, should I subtract from the conjugate base or add to the conjugate base? If I'm adding acid, let's think about this. If I've got moles conjugate base, and I've got my moles acid, I'm going to subtract, I'm going to add moles weak acid, right? So because I'm adding an acid, I'm going to react my conjugate base dependent on how many moles of strong acid I add. And in that process, I'm going to be making more weak acid. So I'm going to have plus moles of weak acid there. Right, this is the equation that we had Monday in class. This is the equation that we had Monday in class. We said normally this moles of conjugate base at the start is 0 because we're just doing a titration. However, in this case, this equation, which combines our equilibrium from the Henderson-Hasselbalch and includes our stoichiometry, essentially allows us to do some shortcuts. So now I'll do buffer A, and then I'll let you do the rest because it's just the same thing over and over again. Once you understand this equation, if you still think this equation is magical, don't use it. Keep doing the reaction and equilibrium tables until this makes sense to you, because if you try to blindly use this, you'll use it at the wrong times and you'll get completely wrong answers. Or you'll plug in the wrong numbers in the wrong spots and you get completely wrong answers. And you'll be like, oh, but you said it would work. And it's like, only use it once you understand it. If you can't derive this equation, you probably shouldn't be using it. Right? Because deriving it is just doing the problem. And then saying, oh, the problem's the same every time. I'm tired of setting up the stoichiometry table every time and the equilibrium table every time. So I'm just going to use this. So let's go ahead and do, this is 13 part B for buffer A. Find the pH of each buffer after 0.1 moles of HCl is added. So this is 13 part B. I'm just going to do it for buffer A. Essentially, all I'm doing is I'm changing my ratio, right? So instead of having 1 to 1, I'm going to have 1 minus 0.1 divided by 1 plus 0.1. That's going to be equal to 0.9 divided by 1.1. Now it's easy. I take that, plug it back into my Henderson-Hasselbalch, I'm done. Hey, I know I said I was just going to do A, but let's do B while we're at it. I'm going to have 2 minus 0.1 divided by 1 plus 0.1. That's going to be, 2, right? That's going to be 1.9 divided by 2.1. Plug that into my Henderson-Hasselbalch, I'm done. Right? This problem probably seemed really complicated to all of you. Right? This problem probably seemed like total magic. But notice, by understanding how the stoichiometry works, and understanding how the equilibrium works, this is actually a really fast, not very difficult problem to do. So having this understanding makes it so this problem that seemed like it was going to take, I was like, oh, how long is this problem going to take me? After I started doing it, I was like, oh, actually, this is going to be really quick. Which is also part of the reason why I was like, oh, I can't put this on the quiz. It's going to take too long. And then I looked at it. I was like, actually, no, this is a really quick problem if we understand what's going on. If we don't understand what's going on, it's impossible. That's true of anything. Question?
Can you just run over the 0.1, like the ratio?
Yeah, so this is because in part B it says find the pH of each buffer after 0.1 moles of HCl is added. So right, the 0.1 is because the problem says 0.1 moles of HCl is added. So my moles of acid here is 0.1, and then my reaction step is minus 0.1, plus 0.1. And so I'm doing my moles of conjugate base minus 0.1, my moles of weak acid plus 0.1. I've changed my ratio of conjugate base to weak acid, which is going to change my pH. Question there, then here.
How's it going to change if you have base instead of acid?
Ooh, good question. Let me see. That gets to part D. So let me see. Is your question
So you
about this
just
first?
take this and then plug it in right there?
I already did the math, right? So notice I've got my 1 minus 0.1 divided by 1 plus 0.1.
Right.
So I solved this whole thing already, and I can just plug that. I can plug 0.9 over 1.1 directly back into the Henderson-Hasselbalch. Yeah.
Okay. And then pKa is still...
pKa has not changed.
Right.
So, any questions? And then finding percent change is just saying, the one with more concentration is probably going to have less change.
Wait, why is like the reactants over the product?
Because remember when we did the equilibrium, right, it flips it, right? And this is from the equilibrium, but we've plugged the stoichiometry into the equilibrium, right? That's why I say be careful with this equation because there's a lot of things happening. The biggest place where people make mistakes is when we change what we're adding. When we start at the beginning of a titration, a lot of people leave the moles conjugate base start 0 all the time because they always get used to just doing it for a titration problem. But this is adding to a buffer, so it's a little bit different. And then when we switch to doing weak basis, strong acid problems, we can actually get away with using the same equation, but people try to do all these weird flips and changing things, and they make some mistakes. So how does this change if we go to part D, and instead of adding an acid, we add a base? So that's going to change. It's not technical. Let's just redo all of this on the side. So that's going to change what our reaction is, right? Part D, we're saying, okay, now I'm going to add base. I'm going to add OH minus. What's OH minus going to react with? NH4 plus to form NH3 plus H2O. I can then do my start reaction. Whoa, that's a weird looking E excess, and then I can set up my equilibrium. And the equilibrium I set up, we still want it to be for NH4 behaving like an acid, and as long as we're in the buffer region, we can make that choice. So I'm going to set it up for NH4 plus H2O goes to NH3 plus H3O plus, right? Same system as before. The change here is I've got my moles, weak acid, moles, conjugate base. I didn't give myself quite enough space, but moles, strong base. So notice we have to be really careful. We have to start being really careful with our labeling. Even though we've been doing, and this has been true for about a week already, even though we've still been doing the same mathematics, now that we're dealing with conjugate systems, everything we're looking at, we've got a weak acid, a conjugate base, a weak base, a strong base, like there's a lot of different parts moving. So we have to be a lot more careful with our labels and make sure we understand the definitions of those terms and make our labels correctly. I'm just going to go ahead and say, the moles of strong base in this case, this is for part D. It tells us again that the moles of strong base is 0.1 moles. So I'm going to have minus 0.1, minus 0.1, plus 0.1. Notice what's changed here. I still have, oh, I had a mistake here. No one caught it. Yikes. This is, if you wrote down moles of weak acid here, not moles of strong acid, how dare you not correct me? You don't add more. If I add moles of weak acid to moles of weak acid, that doesn't make any sense. And you notice over here, I didn't even do, even I pointed at the equation like 6 times. I did the right thing mathematically every time, but I had the wrong thing written down. So if you didn't catch that, this should be moles of weak acid plus moles of strong acid. Now, when I switch to a strong base, here's what changes. Right? So in my buffers, I still have the same moles of weak acid and moles of conjugate base at the start, but now I'm subtracting, because I'm adding a base, I subtract from the weak acid, and I add to the conjugate base. And that's when I'm adding a strong base. And that change should make total logical sense, right? When I add a base, it reacts with the acid, so the acid number should get smaller. When that acid reacts, it creates more conjugate base, so the conjugate base number should get bigger. So I end up with a plus and a minus. Again, if what I just did seems like magic, keep doing the reaction, keep doing the equilibrium until you've done it so many times that it looks obvious to you. It helps when you know what you're looking for, so you know what you're looking for, keep doing it till it seems obvious. So part D is really just the same thing. Yeah?
Do you think you could go through it like the long way? Because I'm still kind of confused. Like,
Yeah, let's go ahead. Let's do one of these the long way. Let's do buffer B adding 0.9 moles. So that is to say we are going to do one the long way and see if we can derive this equation. I'm going to switch it back to the original method. So I'm going to be doing minus strong acid plus strong acid. Strong acid. And let's go ahead, let's see if we can figure out if we get that doing it the long way. So we're going to do part of problem C for buffer C. Oh, I want to do it for buffer B. I think buffer B will look more neat. So, part C says find the pH of each buffer after 0.9 moles of HCl is added. So doing part C, for buffer B, we have 2 molarity at 1 liter for our NH3, and we have 2 molarity at 1 liter for our NH4. The reason that it matters that it's at 1 liter is because we're going to do a reaction. A reaction when we're adding acid is going to be the HCl plus NH3 goes to NH4 plus Cl minus. We could get some H2Os and stuff in there as well. I'm going to do my start reaction excess. My HCl is 0.9 moles. My NH3 is 2 moles. And notice I've also got some starting NH4 plus in this case. 2 moles. The Cl doesn't matter, just like H2O doesn't matter, right? Technically, we could take this HCl and just call it H3O plus. Cl is going to be a spectator ion, and when we put HCl in water, it completely disassociates. Whether you put it as HCl or H3O plus, I'll accept it. It's probably going to be more consistently easy if we just call it H3O plus and call this H2O. Again, we don't care about the H2O though, right? Either way works. I'm just using, the reason I can switch it to H3O plus is because of the definition of a strong acid. Strong acid completely disassociates.
I'm sorry, why was the 0.9?
That's defined in the problem.
Oh, okay.
The problem says we add 0.9 moles of H3O plus or HCl. I can tell by looking at the 1-to-1 ratio that the 0.9 is my limit. So I'm going to do minus 0.9, minus 0.9, plus 0.9. This will give me 0. I'm going to leave it a little bit in an unevaluated way. 2 minus 0.9 and 2 plus 0.9. And you can see, again, looking at the pattern of what I'm trying to recreate, you can kind of see why I want to leave that unevaluated. I can then say the molarity resulting from this. And again, I'm gonna be a little bit cheeky. 2 minus 0.9 divided by volume total would give me my molarity. And 2 plus 0.9 divided by volume total would give me my molarity. And now look at this and say, okay, I want pH. I get to pick, since I'm going to have some NH3 left in solution and I'm going to have some NH4 plus left in solution, I get to pick which equilibrium I look at. Which one's going to be easier? The base equilibrium or the acid equilibrium? Yeah, it's going to be the acid. Why is the acid easier?
Donate a H plus to water.
It's gonna donate an H plus, and the reason that makes it easier is because the problem is asking us to calculate the pH. Right? Since we're almost always being asked to calculate the pH, it's always easier when we have H3O plus as a product. And so if we get a choice, we almost always choose H3O plus to be a product, so we're finding the pH. So I'm going to go ahead and set up my equilibrium. I'm going to set it up as H2O plus NH4 plus goes to NH3 plus H3O plus. Notice I've got my H3O plus as a product, so that's going to make it a little bit easier. I'm going to have a Ka associated with this that I calculated earlier. I'm going to set up an ice table for this, where I'm going to use 2 minus 0.9 over volume total, 2 plus 0.9 over volume total and 0. I'm going to have minus x plus x plus x. I'm going to use the x's small approximation, right? Ka is 5.5 times 10 to the minus 10. I should still be able to use the x's small approximation in this equilibrium table. So I'm just going to be, oh wait, this is 2 minus 0.9. It's not just the 0.9 that's divided, it's the whole thing.
Is it NH4 also 2 plus 0.9?
Oh, ooh, did I mess it up? Oh, I so did mess that up. Notice, even if you've been doing this for 4 years, like, I've been teaching this class for over 4 years, you still make mistakes. Make sure you pay attention. The reaction flipped, and I forgot to flip my plus and my minus. The NH4 is the thing that is increasing, so that should be plus. The NH3 is the thing that is being reduced, that should be the minus. Thank you for catching that. Then at equilibrium, I'm going to have 2 plus 0.9 divided by volume total, and 2 minus 0.9 divided by volume total, and x. Where I'm going to go ahead and just say x is my H3O plus concentration that I'm trying to solve for. Now, when I set this up for my Ka, I'm going to have Ka is equal to H3O plus times products over reactants, right? I'm going to have 2 minus 0.9 over volume total and 2 plus 0.9 over volume total. What do you notice about the volume total? Cancels out. Cancels out when I make the ratio. And you can see how close we are to getting this equation now because I left it unevaluated, right? I've got my moles of conjugate base at the start, 2, minus the moles of strong acid added, 0.9. I've got my moles of weak acid at the start, 2, plus my moles of strong acid added, 0.9. Same thing we did in class on Monday, right? So at this point, we could solve for H3O plus right here, but the problem's asking for pH. If I take the negative log of both sides, I'm going to get pH equals pKa plus log 2 minus 0.9 divided by 2 plus 0.9. We got that equation in green. If you're still like, whoa, that seems magical, do it again, right? We do so many buffer calculations over the next 2 weeks with the lab, with what we do in class leading up to the midterm. We do so many buffer calculations. You've got plenty of opportunities to like practice this and get it to start to make sense.
So like, is this the type of stuff that this quiz is on, like buffer stuff, or more like titration?
Same.
Same. Oh, okay.
Right? Those are really the same
But
thing.
like these types of problems.
These types of problems where we're like adding and seeing how it changes. I mean, honestly, I wish I could have the quiz cover everything, you know. Realistically, I'm gonna try to put as many varied problems as possible and make sure that I cover as many things as I can in like a 15-20 minute quiz. So I'm not going to be able to fit everything on there. But we've gone over this equation. We should be able to use this equation even if it doesn't totally make sense to us. And we should be able to do these calculations. Yeah?
I'm kind of confused how you got from the Ka equals the concentration of H, that stuff. How did you get from there to the...
So when you take the negative log of both sides, you get negative log of Ka is pKa, negative log of H3O plus is pH, and negative log of the fraction is just the negative log of the fraction. And so I just added the fraction over. And then flipped it so it looks the way I want it to. Oh yeah.
Thank you.
So I think that covers enough of problem 13. And can I see something real quick? I want to see number 14. Number 14 is another really long one. Number 14 will not be on the quiz, but you shouldn't cross it out. You should still do it. Number 14 is essentially your lab. The lab you're doing this week in the buffers lab. Make a buffer. How do you make sense of your buffer? How would you make it if you could use any materials? How would you make it if you were doing a titration problem?
Morgan, whenever this equation class, like it was like a 0 right here, so like what's the difference between like that? Because you said it's mostly like that.
So, and I did specify that, and I said be careful about it, right? Because it's not always 0. It's 0 a lot of the time, because a lot of the time when we're using this equation, we're doing titrations, right? And when we're doing titrations, we're starting with 0 conjugate base on all weak acid, so our starting conjugate base is 0. But whenever we are reacting a buffer, the conjugate base at the start would not be 0. And I wanted to make that explicitly clear in class on Monday, because that is the #1 mistake people make on their post lab for the buffers lab, is they don't know what to do with the initial concentration, the starting concentration of the conjugate base. They just leave it 0 because it's always been 0, and then it ruins their calculation. I'm going to skip number 14 if that's okay. It's not going to be on the quiz. It's something you should be able to do because you had to do it for lab this week. It does use the idea of total concentration. We can do it in office hours on Thursday, Friday, or next Wednesday. Because, again, it is worth understanding, but it's not going to be on the quiz today. And let's get to problem 15. And for problem 15, I'm going to leave this equation in the square there up, because pretty much every calculation we're going to do on homework 4 and homework 5, and I think even part of homework 6, this equation is probably going to be handy. Until we get out of the buffer region.
Is that equation on the equation sheet?
I don't think so.
It says it in like a simpler form. It says it conjugate base over weak acid, but it doesn't include it.
Yeah, so Henderson-Hasselbalch equation is on there, but not the one that also includes the stoichiometry, which I kind of made this equation up, but it's just combining things. The reason that you don't see that in the typical Henderson-Hasselbalch is because the typical Henderson-Hasselbalch is used for biological sciences, where they don't really care about the stoichiometry, they just care about the ratio to get a target pH. You know, if you've got a protein that folds or unfolds at a certain pH, after you identify that target pH, all you care about is making a buffer to get that target pH. You don't care how you make it. In the chemistry class, of course, we care about how we make all that stuff.
So that's when you're adding an acid, right?
Yeah, so right now this is set up for adding an acid, which is going to react to the base and produce more weak acid. Problem 15, if I remember correctly, is a giant titration problem.
Yeah.
What's the acid, the Ka initials, and all that stuff?
You titrate a 50 milliliter sample of 0.04 molarity.
0.04 or 0.0.4?
0.04.
That's a low molarity.
And the Ka is 1.4 times 10 to the 4. With 0.16 molarity of potassium hydroxide.
Huh, okay.
And Jay is asking what volume of titrant is needed to reach a pH of 3.22.
Right. And this is one of the problems I warned about. Doing this target pH problem backwards is a little bit tricky. Right, so normally what we would do, I'm gonna do it the typical way, where let's pretend we don't have this equation in green, which is gonna make our lives a lot easier. What we have to do is we have to say pH equals pKa plus log, I'm just gonna call it conjugate base to weak acid. I'm going to do some subtractions. I'm going to do 10 to the power of pH minus pKa equals my ratio of conjugate base to weak acid. So we can do that math. That gives me the ratio of conjugate base to weak acid, which gives me 2 unknowns. But then I can recognize that I can get these from stoich. where I can set up the problem that we're adding base, right? So we've got OH minus plus HA goes to A minus plus H2O. I'm going to do start reaction excess. I'm going to have 0.16 times some unknown volume. That's what I'm trying to solve for. I'm going to have 50 times 0.4. I'm going to have 0. I'm going to have minus 0.16V minus 0.16V plus 0.16V. I'm going to have 0. I'm going to have 50 times 0.4 minus 0.16V, and I'm going to have 0.16V. So then I can say my ratio is equal to this, and I can plug that all together, right? And what I want you to realize is if we put that all together, right? So this is the typical process. The first 2 years I taught the class, this is how I taught everyone to do it. This is how I did it. And after doing it that way for 2 years, I was like, man, there's got to be an easier way to do this, because explaining like the backwards thinking of like I've got too many unknowns and I've got to figure out like I've got 2 unknowns here, I've got to eliminate my unknowns, it's driving me nuts. And that's kind of how I came up with this, right? So if I just put this all together, notice I've got my stoichiometry here. I can put this as pH equals pKa plus log 0, because I start with a 0, plus 0.16V divided by 50 times 0.04 minus 0.16V. I can just go right to this idea, say my moles come from volume times molarity. I've got one unknown in this equation. I know the pH that I want to get. I know the pKa that I'm using. I'm just solving for volume, right? We don't actually have to do it this way every time. And I actually find the backwards thinking, while the mathematics makes sense, the chemistry kind of, I feels like, is a little bit hidden when we do it that way, when we're just understanding the mathematics. But the whole idea is, I've got to get the correct ratio of conjugate base to weak acid to control my pH, right? That's what we're doing all the time with buffers. We're getting the right ratio of conjugate acid to conjugate base to weak acid to get a particular pH. Yeah.
So could we do it the same, kind of a similar way, but do M1 V1 equals M2 V2 to start, and then like find the actual numbers and then plug it into it?
You can't do M1 V1 equals M2 V2 because we're not getting just to the midpoint, right? We're not getting to a point where the moles are equal to each other. We're getting to some ratio that gives us the correct moles. So
then,
we are using molarity of strong base times volume of strong base, molarity of weak acid times, I forgot my 0 again, 0.4, 0.4. We're using our molarity of weak acid, volume of weak acid, so that's molarity times volume is still coming up just to get us to our number of moles.
Yeah.
And what I love about this equation, which I kind of rewrote for the problem in black there, is that equation does all of this stuff. Right? And that's where I'm saying don't have this equation be magic. Make sure you can make sense of this.
So then how would we like go about solving that?
So let's go ahead and actually solve it now. So the target pH was 3 point something or other?
3.22.
3.22. What's the pKa?
I got 3.9.
Makes sense. 3.9 because it's almost times 10 to the minus 4. So about 3.9. Okay. Plus log. I'm just going to leave this as an open parenthesis for now, but it's got all that junk in there. And you're going to notice we're going to do all the same mathematical steps, but I find this just kind of cleaner. Right, so I'm going to do 3.22 minus 3.9 is negative 0.68. So I'm going to have 10 to the negative 0.68 equals my ratio. Please check my math. I also can't do 10 to the power of 0.68 in my head. I know it's going to be between 0.1 and 1.
What was the question?
What's 10 to the power of negative 0.68? And is 0.68 the correct number?
It is, but would we be doing 10 to positive 0.6?
No, because I'm going to do I'm going to do 3.22 minus 3.9. So I'm going to get a negative number. So the reason that it's 10 to the negative 0.68 is because 3.22 minus 3.9 is negative. But notice this is a plus log, so I don't flip the sign because it's a plus log.
Oh, okay. That makes sense.
What's this number equal to? 0.209. I want you to notice something. My pH, my target pH, is lower than my midpoint. So I expect to have less conjugate base than acid, which is why this ratio is less than 1. I expect to have more acid because my pH is lower, and so I expect to get a ratio that is a number less than 1. Now I can go ahead and plug in what that ratio is. I've got 0.16V. What's 50 times 0.04? I'm tired of writing that down. Really? 2 minus 0.16V is equal to 0.209. Solve for V.
And that's the answer.
And that's the answer. That is the volume of strong base you need to add to get to a particular pH. And being able to solve that problem, volume to a particular pH, will be really handy when we start doing buffer capacity calculations. Because a buffer capacity calculation is essentially doing this twice.
I have a general
Wait.
question.
So to cancel out the log, is that what you did 10 to the negative
Yep.
168?
Yeah.
For 16, it's asking the volume of KOH required to get the equivalence point, so it's like the same thing, but with the equivalence point pH.
Yes, however, remember, everything we've been doing, this equation in green and all of the things we've been doing, only work when we are in the buffer range, when we have some amount of weak acid and some amount of conjugate base present, or conjugate or weak base conjugate acid. To get to the equivalence point, we need to go back to the idea of just doing stoichiometry and just doing equilibrium.
Okay.
All of the shortcuts we learned in the last 2 days have all been for the buffer range, and we said it's important that we have those shortcuts because most of the calculations we do are in that range. Other questions? Yeah.
Are we gonna have to know the problems where it says like 2.5% of the acid dissociated?
Yeah.
Can we do one of those?
Yeah, we did one earlier. Essentially what happens is those are all initial pH problems. So that was like problem 4. I think problem 3 does the percent dissociation, but problem 3, you get Ka equals x squared over Ha initial, and you just have to recognize that the percent dissociation gives you x. Right, so percent dissociation tells you how much of your original acid falls apart. If you had 100%, if you started with a 1 molar solution and had 100% dissociation, what would your x value be?
0.
Ooh, 1.
1.
Right, if 100% of your acid disassociates, it all becomes H3O+.
Okay.
If 10% of your acid disassociated, it'd be 0.1.
Okay.
Because only 10% of it falls apart into A- and H3O+. If 0.25% of it dissociates, what if it was a 2 molar acid and 10% dissociated? 0.2. That's it, right? But that logic, and notice the math isn't difficult, but the conceptual idea of what it means to have a percent dissociation That's a little bit more tricky. That's where the thinking comes in.
Okay.
But yeah, those are some of the easier problems on the homework after we get that concept. Without that concept, it's really hard. I have not done problem 19. I honestly can't even think of what problem 19 is right now. No one's asked me about it yet.
So
Oh, question.
we solve for V, that's already in milliliters, right?
Yeah, because we left the 50 in milliliters, so it's already going to be in milliliters. That's an important thing to point out. Notice, I left my my volume in milliliters. That's 2 millimoles, not 2 moles. So when I solve this, my volume will be in milliliters. Good eye. Make sure you pay attention to your units when you're doing this. Again, once we get comfortable with this equation, it's really easy to get carried away with the mathematics and forget about what we're doing. So make sure this is still a physical thing describing a chemical situation. Pay attention to your units.
So it would be milliliters?
It would be in milliliters because I left my 50 in milliliters. I also like it better than doing 2 rather than 0.002. And then it'd be in liters. What was problem 19?
It says for each of the following acids, show which would be useful to prepare a buffer with a pH of 4.5. Justify each answer numerically. And then it gives you acids with their Ka values.
So for that one, we just calculate pKa's, right? And
Yep.
whichever one's closer to that value would be best.
So we want a pKa closer to 4.5.
Yeah, and this was a question that came up. A couple people came by on my office on Tuesday, and one of the things that they asked a lot about was how buffers work, where buffers work, all of that. Essentially, every time, the thing that makes buffers complicated is we're usually creating a buffer to control another system, right? Just having a buffer by itself is kind of boring. We make a buffer to control another system. So what we want to do is we want to look at our system. For lab this week, it's an indicator system, right? And we want to say, in that system, what pH do I want to get to? What's my target pH? After I identify for whatever system, if we're doing a titration, maybe it's the midpoint, maybe it's the equivalence point. If we're looking at proteins, maybe it's a certain pH where the protein folds one way versus another. If we're looking at blood systems, it's 7.2, otherwise we die. But whatever system you're looking at, you determine what your target pH is, and then you say, okay, now I'm going to create a buffer to get to that target pH. And we want to make sure the target pH is near the midpoint of the buffer. I'm going to say that again. We want to make sure the target pH is near the midpoint of the buffer. And notice again, I have to be careful with my vocabulary. I can't just say the target pH is near the midpoint. The target pH is near the midpoint of the buffer system, right? So I have to think about the two systems and which system I'm talking about. Because your target pH might be the midpoint of a weak acid, but not of your buffer. Your target pH might be the equivalence point of a weak acid, but not of the buffer, right? After you define your target pH, you want your target pH to be near the midpoint of your buffer. So for problem 19, all we have to say is, okay, we're given a target pH. Which one of those systems would have a midpoint near that target pH? Because that one will be the best. Definitions, logic, questions.
So you would find the pKa and then you'd want it within, if the pH is 4.5, would you want that within like 3.5 to 5.5?
Yes.
Okay.
So you'd want it someplace between 3.5 and 5.5, as close to 4.5 as possible.
Okay.
And then what we'll talk about today is not just the target pH, but the capacity of the buffer, which we kind of, doing problem 13, we kind of did some calculations related to capacity. Capacity just depends on how many moles of buffer there are, how much acid it takes before you, quote unquote, break your system. Other questions? Anything we haven't talked about yet? Okay, I'm going to go ahead and get this video uploaded so
I have one
people
more
can
question.
watch it. Oh, well, one more.
I have a question. Explain how you choose an acid-base pair for making a buffer solution. Is that the same thing we just
Exact
did?
same thing we
Okay.
just talked about. Find the target pH, so whatever you're trying to buffer at, and then find a buffer system with its midpoint of the buffer near the target pH.
I just had like a small conceptual question, just to make sure I'm right.
Mhm.
For strong acids, to find the pH, would the H plus concentration be equal to the concentration of the strong acid?
Yeah! For strong acids, since we have this approximation that they 100% disassociate, your H3O plus concentration is your acid concentration.
Okay. So that's an approximation, I think?
It's a pretty good approximation. It's a very good approximation because most strong acids have Kas on the order of 1,000,000. So you're looking at like a 0.0001% error.
Yeah.
Pretty good. Question?
I was kind of confused on number 9. It was asking us which would have a higher buffer capacity.
That one won't be on the quiz. We're talking about buffer capacity today. Short answer, more moles, more capacity. So you look at the volume, you look at the concentration. Higher volume is higher capacity, higher concentration is higher capacity. That's the short answer.
What are the pH changes that would affect it too?
Yeah,
Well,
little
in this
bit.
case, it has them both at a pH of 3.
Yeah. So most often we'll have them at the same pH, and then we'll just either change the concentration or the volume, and we'll see that kind of as a quick way to tell.
Okay.
But yeah, because the capacity comes down to the stoichiometry, and we're going to talk about that today. More moles is more capacity. Is the short answer. More moles is more buffer capacity. So then we just have to say, how do we get more moles? Well, increasing the volume at the same concentration, not by adding water, but increasing the amount of buffer we have without changing the concentration, that would give us more moles. Or keeping the same volume and increasing the concentration, that would also give us more moles.
I had a question about the equation.
Yeah.
It says moles of that's conjugate base. Right?
So moles of conjugate base at the start?
At the start.
Yes.
Okay.
Right. And the problems we did in class on Monday, we didn't have any moles of conjugate base at the start.
Right.
But in
that
problem,
was the 0.
yeah, that was the 0.
And this is the one for when we add an acid.
Yeah, so we're subtracting from the conjugate base and adding to the weak acid because
That's
we are
because you're reacting with the conjugate base, so
Yeah.
it gets rid of that and then
Yeah.
gives you more of the weak acid in the end, right?
exactly, because in this case we are putting a strong acid into our buffer.
Yeah.
And then the signs flip if we put a strong base into our buffer.
Thank
Great.
you.